Good afternoon. This is your fifth digital class for the subject physics. Now, in our last class, we discussed about Coulomb's law and related expression. Now, today we are going to discuss few application of Coulomb's law as well as the next topic, that is electric field and electric field intensity. So, let me discuss the application. Number one application. Number one, charges of 1 microcoulomb, 2 microcoulomb, minus 3 microcoulomb are placed at the corners of an equilateral triangle of side 4 cm. So this is your equilateral triangle, and these charges are placed at the vertices of the equilateral triangle. So charges are 1 microcoulomb, 2 microcoulomb and minus 3 microcoulomb. What it says, at the corners of an equilateral triangle of side 4 cm. So each side is your 4 cm. So as it is an equilateral triangle, each angle is your 60 degree. Now what is asked to find? What is the magnitude of the net force acting on the charge? Minus 3 microcoulomb. So this is your charge, minus 3 microcoulomb. Now in our last topic, Coulomb's law, we said that if we place any two charge, then definitely there is a force, and that force experienced by each of these two charges. So here is also, if we consider these two charge, 1 microcoulomb and minus 3 microcoulomb, so definitely we will experience a force due to the charge minus 3 microcoulomb, as well as minus 3 microcoulomb will experience a force by the charge 1 microcoulomb. So as it is says that force on the charge minus 3 microcoulomb, so the force on the charge minus 3 microcoulomb due to the charge 1 microcoulomb is along RP, and it is specified by the arrow, and here we have symbolized that one is your F1 vector. Now again, if we consider this charge 2 microcoulomb, so this is your positive, this is your negative. So again, this charge minus 3 microcoulomb will experience a force F2 vector, and it directs from R to Q. So the force is attractive. So what we have to find? We have to find the resultant force on the charge minus 3 microcoulomb. So two force, one is your F1 vector, another one is your F2 vector. So you see the expression, we have used the expression Coulomb's law. So F1 vector, this is the magnitude part, and the expression is your K Q1 Q2 by R square. So K is your constant, 9 into 10 to the power 9. So this one is your charge, minus 3 microcoulomb. We have considered the sign as it is a vector quantity. Minus 3 into 10 to the power minus 6. 1 microcoulomb is your 10 to the power minus 6 coulomb. So again 1 microcoulomb here, 1 into 10 to the power minus 6. And that one in denominator part, it is your distance. So distance is your 4 centimeter. So you have to convert that 4 centimeter into meter. So 4 into 10 to the power minus 2. So as it is R square, so you have to square it, and it directs from R to P as it is specified in the figure with F1 vector. So if we simplify this one, it comes out minus 3, and as it is square, so it should be your 16. So minus 3 by 16, and this is your K, and 10 to the power minus 6, 10 to the power minus 6, 10 to the power minus 12, and denominator is your 10 to the power minus 4. So if you take 10 to the power minus 4 up, it goes to 10 to the power minus 8 Newton. So similarly, you can find force F2 vector, and it is your K, this charge, minus 3 into 10 to the power minus 6 coulomb, and this one is your 2 microcoulomb, 2 into 10 to the power minus 6 coulomb, and denominator part is your distance. Then the distance is nothing but is your 4 centimeter. That is your 4 into 10 to the power minus 2 meter, and it is a square, so you have to square it, and it directs along from R to Q. Now if you simplify this one, it comes out to be your, if you simplify 2 here, 4 square, it means 16, 2 and 16, it means 8. So minus 3 by 8 K into 10 to the power minus 8 Newton. Now what you have to do, you have to find the resultant force of F1 and F2. So you have to use the vector addition. So if we consider these two vectors as the two adjacent sides of a parallelogram, then this is nothing but is your diagonal. So the diagonal gives the resultant of these two vector, F1 vector and F2 vector, and the angle between F1 vector and F2 vector is your 60 degree, because it is an equilateral vector. So if you use the vectorial addition formula, that is your parallelogram law, it comes out to be your F equal to root over F1 square plus F2 square plus twice F1 F2 cos of angle between F1 vector and F2 vector, that is nothing but is your 60 degree. So this simplified part I am leaving on you. You just substitute this value and try to simplify by considering the magnitude F1, F2, and try to find out the value, and the value comes out to be approximately 44.65 Newton. So this part I am leaving on you. You substitute the value and find the resultant force. So this is one application. So This is your simple diagram. Now next application, this one, point charges having values 0.1 microcoulomb, that's a positive, 0.2 microcoulomb, minus 0.3 microcoulomb, minus 0.2 microcoulomb are placed at the corners A, B, C and D respectively of a square of side 1 meter. So you see this figure, this is your square A, B, C, D, and these are the charges placed at the corners of this square. So what you have to find, calculate the magnitude of the force on charge plus 1 microcoulomb placed at the center of the square. So you have to find out the center of the square. So center of the square is nothing but the intersecting point of the diagonal. So this is your intersecting point of the diagonal. So this is your center of the square, and here you have to place the charge 1 microcoulomb. So what you have to find, you have to find the force on 1 microcoulomb by each of these charges which you have placed at A, B, C and D. Now here you see, if you consider the direction, suppose here plus 1 microcoulomb and this is also plus 0.1 microcoulomb. So force on plus 1 microcoulomb is nothing but F1 vector which you have specified from A to O, because it is your repulsive force. So similarly, if we consider this charge plus 0.2 microcoulomb, that is also your repulsive force which is symbolized by F3 vector, because this is positive and this one is also positive. Now if you consider this one minus 0.2 microcoulomb, so if we consider this one is your 1 microcoulomb charge and another charge is your minus 0.2 microcoulombs, and definitely it is your attraction, because this is a negative and this one is a positive. So this vector F3 vector gives you the direction. And similarly, if you consider this 1 microcoulomb and minus 0.3 microcoulomb, so definitely it is again attraction. So these two forces, F1 vector and F4 vector, is in same direction, and again this force is your F3 vector and F2 vector, it is in same direction. So the resultant of F1 vector and F4 vector is nothing but is your F dash vector. Similarly, the resultant of F2 vector and F3 vector is nothing but the vector F double dash vector. So what we have to find, we have to find the resultant of this F dash vector and F double dash vector. So F dash vector is along this direction if you consider the resultant, and F double dash vector is along this direction. F1 F4 is along this direction, and F2 F3 is along this direction. So the angle between these two vectors is your 90 degree. So if you use law of vector addition, then the simplified resultant magnitude comes out to be your F dash square plus F double dash square plus 2 F dash F double dash cos of 90 degree. So cos of 90 degree is 0, so that part goes off. So you do have F equal to root over F dash square plus F double dash square. Now this is your ultimate formula which you have to find it out. Now for that you must have to know F dash as well as F double dash. Now how can we find F dash and F double dash? F dash is your nothing but is your F1 vector and F4 vector. So F1 F4, so F1 F4 both are in same direction. So if we apply the law of vector addition, then magnitude of F dash vector is nothing but is your sum of the magnitude of F1 and F4. So F1 is your this one, so force between plus 0.1 microcoulomb and 1 microcoulomb. So you substitute this one Q1 Q2, and what is the distance? This one, this part we can show it here, please show here. If we consider this triangle here in the diagram, ADC is your right angle triangle. So if you have to find AC, then you have to use the Pythagoras theorem, that is your AD square plus DC square. So each value is your 1 meter as specified in the question, so it comes out to be root 2. Now as it is half of AC, that's why you will get OA equal to OC equal to AC by 2. AC is your root 2 by 2, that is your 1 by root 2. So here what we have to find, we have to substitute the distance OA, distance between the two charge, and it comes out to be 1 by root 2, so it should be 1 by root 2 square. So F1 is your this one, and F4 you can get by considering this one and this one. So as we are considering the magnitude, so we are not considering the sign. So 1 microcoulomb 1 into 10 to the minus 6, and this one is your 0.3 into 10 to the minus 6, 1 by root 2 square. So if you simplify this one, check the simplification part, you will get the resultant force is your 72 into 10 to the minus 4 Newton. So the resultant force, that is your F1 and F4, is your 72 into 10 to the minus 4 Newton. Similarly, if you proceed for F double dash by substituting the values, you will get 72 into 10 to the power minus 4 Newton. So check this one, I am leaving on you. So after that you can get the resultant force by substituting here, and after substitution the value which is coming out, that is your 0.01018 Newton. So check this calculation. This calculation part I am leaving on you. It's very simple. So these are the two applications. More we'll discuss in next class. Let me go for a topic, and as we have discussed the Coulomb's law previous class, so today we are going to discuss the electric field. Now if you place a charge, what will happen? Some influence creates or some influence surrounds the charge, is not it? And that influence region is nothing but the field. So as specified in the statement, the region or space around a charge body or a point charge within which its influence can be felt by other small charge is called electric field. So if you consider this one is your source charge, so definitely a region will create around that source charge. So if you place any charge within that region, then definitely that charge will experience some kind of influence. If you place that charge out of that region, then there will be no influence. So here we are considering a point A within the field of the source charge, that is plus Q, and we have placed a test charge plus Q naught at that point A, which is within the field of the source charge. So what will happen? A force will experience. This is your repulsive force. The direction is this side. Force experienced on the test charge by the source charge. So this force is experienced on the test charge Q naught. So as we are trying to define electric field intensity, so we'll go to the expression first of all. Statement basically. The electric field intensity due to a static source charge. This is your static source charge at any point in its electric field. A is your point within the electric field. Is defined as the force experienced by a unit positive test charge at that point. So what you have to do, you have to place a unit positive charge at A if you have to define the electric field intensity at A, and then what you have to do, you have to find the force on that unit positive charge. But practically unit positive charge is very tough. So what we do basically, we place any test charge. Suppose here we have placed test charge Q naught. Definitely this test charge magnitude is very less compared to the charge capital Q, which is your source charge. So we used to find the force on the test charge Q naught by unitary method. So then by unitary method we used to define the force on the unit charge. So first of all, what is the force on the test charge? If you consider F is the force on the test charge Q naught by the source charge, then what is the force on the unit charge by the source charge? So this is nothing but is your F vector by Q naught by unitary method. So F vector by Q naught is nothing but is your field intensity. So as two quantity is your vector, one is your F vector, E vector. So what is the direction of E vector? Same as the direction of F vector. So more precisely you can define this expression by considering limit Q naught tends to 0. Why we are considering Q naught tends to 0? Because if we consider a source charge, so definitely a field will create surrounding that source charge. So if we consider any other charge within that field, then definitely some field will also be there due to this test charge. But we are supposed to find the field intensity due to the source charge. So how can we eliminate this field that creates by the test charge? By considering the test charge should be very small, so that we can neglect the field created by the test charge. So that's why we are considering the limiting case, limit Q naught tends to 0. If the charge is very less, the test charge is very less, then definitely the field due to that test charge can be neglected. So limit Q naught tends to 0 signify that the field intensity at A is due to only source charge plus Q. Now let me go for the expression. This is your diagram, previous diagram, same as this one. Source charge, test charge, distance is your R, force is this one, field is this one. So Coulomb's law, if you apply, then you will get F equal to K Q naught by R square. So if you are interested in defining the field intensity at A, what you have to do? You have to place a test, you have to divide the force on the test charge by the test charge. So E is your F by Q naught, so it comes out to be your KQ by R square. So this expression shows that field intensity is independent of the test charge. It depends only on the source charge. Now let me go for the physical significance of electric field. It says that electric field intensity at a point represents the magnitude and direction of the electric force experienced by unit positive electric charge placed at that point. So definitely if we place the test charge here, so definitely the direction of the force can be defined. Once we can define the direction of the force, then definitely you can define the direction of the field by using this expression. So let me go for the note part. Electric field is a vector quantity. Basically electric field intensity. Let me to correct. Electric field intensity. Electric field intensity is a vector quantity and its direction is along the direction of the force. Now regarding the dimension, this one dimension for electric field intensity equal to F by Q. So F for dimension is M1 L1 T minus 2 and this is your AT. So if you simplify M1 L1 T minus 3 A minus 1. So this is the dimension for the field intensity and the unit definitely Newton per coulomb. So some more part I have given here. Number 4, vector form of field intensity. You can define the vector form of field intensity because all of you know the vector form of the Coulomb's law. So what you have to do, you have to consider that Coulomb's law, and out of that two charge you can consider one as your source charge, another one is your test charge. So if you consider one is your source charge, another one is test charge, you can define the field intensity at that respective point by dividing that expression for the force within by the test charge as per the definition for the field intensity. So this is all about for this digital class, that's which is number 5 digital class. So more we'll discuss next class. So if you have any doubt, any query, please put your doubt on the WhatsApp group so that I can give the answer. Thank you.